Just do it. It'll turn out okay. And welcome to our penultimate episode of Before Earth, because I think we're still I'm confirming this right now. On June 22nd, we'll be having a follow-up Q&A for our finale.
I think so.
Sure.
We're gonna have a follow-up Q&A. Yes, we'll have a follow-up show. Well, that'll be the after show.
Yes, but while we're waiting for the slides to finish,
It's done. The upload is finished.
Oh, perfect timing.
You're good. All right. So why don't we introduce everybody?
From the top, right? Or
First come, first serve.
Well, I'm on top.
All right.
I am I am Michael Vandergraff, also known as Dr. Tapioca Weasel. I'm a physicist, but I'm not an astrophysicist. So yeah, great to be here.
And I go by the name of Neslik, but you can call me Nes for short. And I'm not an astrophysicist or physicist at all. I'm more of a biologist, but I'm very interested in learning stuff about the universe and cosmogony and such. So eager to learn about this.
And I'm Landon Knoll. I wish you a good morning, good afternoon, or good evening, depending on your time zone and latitude, from your astronomer guide to our favorite universe. And we have a fun show today, BE4. There'll be a BE after show thing later. I think we've set that date. Or have we?
June 22nd. I think it's June 22nd.
Yeah.
Because Vandy is unavailable on the 15th.
That is correct. So, what? That's June 27th, right?
Second.
22nd. All right.
YouTube.
Excellent. And that's going to be at. All right. So let's get started on this. So we have BE4, and we'll go over. Saying I need to, I guess, present that. Am I doing the presenting?
Oh, I think you're all the way at slide 2 right now. You need to move down all the way down to BE4.
How do I do? I only have button clicks.
Yep, that's how you have to do it.
Going over to 100 slides. Oh dear.
This is why we usually start doing this ahead of time.
That's interesting. It takes longer to load. There we go.
Yeah, it takes longer to load than for hadrons to form in the early.
Well, also it was rendering on YouTube. I can see it rendering on YouTube, even though for me it needed a split second, so I didn't see the slides.
Yes. Well, it's what it is. It's what it is. What can you say? Nice technology. Anyway.
So in this episode, the star of our series is finally going to arrive at the end.
Yes, literally, our star, our sun, and our moon. And if we look at where we are or we have been in the show, we're in BE4. So maybe if you remember, BE0 was was talking about the Big Bang process. BE1 in this nice logarithmic scale showed you all of the various exotic things that occurred, and roughly the first second or so of the universe. And then BE2 ran through the photon epochs and so forth, moving up to the first 100 million years. And then BE3 had some more interesting things where we have moved on to galaxies and stars and their star evolution. Now today, if we go into, click. So this is where we are now. From a linear standpoint, we are looking at this last section of things when interesting stuff happens, such as the formation of the Earth and our solar system. So we're going to have this show today. We'll have a after show, as mentioned, scheduled on the. Remember again, it's on June 22nd.
Yes.
At the same time, and this will be a time for us to do. We'll just do an extremely brief recap of the history of the cosmos, and then sit back for your questions. So, if you can't make it there, please leave your questions in the comments below, down there, and we'll get to them. Otherwise, if you happen to be able to join us live at that time, you can ask additional questions about our wonderful universe. So let's move forward.
All right.
Did it click? Come on. Click again. Let's do 109. Okay, there it is. Okay. So we'd like to review, first of all, about supernovae. And in particular, we want to mention that render. So if you remember, we discussed the how the life cycles of stars, and we indicated that they typically end up in one of several ways. They can be stars run out of fuel and collapse and form a white dwarf with enough mass. They get higher and higher temperatures where the internal of the core causes weird things to happen, and for those stars that manage to start to fuse iron, because that fusion process takes in energy. It's endothermic rather than exothermic, gives off energy. You get a runaway collapse, and you get resulting of either a supernova that typically produces either a neutron star or a black hole. Those supernovae also eject lots of stuff into space, and the shock waves hit things, and the hitting of the things that they hit do interesting stuff. And that's part of what we're going to be talking about today. Other comments? So, other thing we want to mention is neutron stars. And you might remember that neutron stars are important, particularly when they collapse. So neutron stars, remember, can be one of the things that can happen when massive stars collapse, running out of fuel at the end of their lifetime. And when neutron stars collide, they do lots of things besides generating lots of gamma ray jets and so forth. Go ahead.
I think one thing we forgot to mention before is like binary star system. Like I believe many, in fact, aren't most stars part of a binary system? Most, right?
Yes, they're and they can. Those things can. Binary stars have a particular pathway that's different than the. I guess the important thing to remember is that however the supernova happens, the shock waves produce, induce gas clouds to begin to collapse when they hit them. Mm-hmm. In the case of neutron stars, it doesn't matter how it gets there. The shock wave causes the star to form because we're on star formation. In the case of the other thing, however, is that their neutron stars have an additional process that's I think is rather important to consider, and that in addition to them creating very energetic jets, they will also generate lots of the heavier elements, and because most of the heavier elements in the periodic table actually come from a combination of either supernovae or neutron star collisions. So if you look at this typical periodic table, you're seeing that the neutron stars are the things in orange that are generating lots of heavy elements. They're also dying low mass stars as well that can generate certain things. But the point is that a lot of material that gets sent out in these supernova shockwaves out into the universe come from combinations of the supernova itself and neutron star collisions.
I can see that like most of your silver and gold is from neutron star collision. It's pretty
Yes.
amazing to realize that, like the gold, like if you have a gold on your ring finger or something like that, that stuff literally came from that
Yeah.
event.
Yes. So those neutron stars, which are the result of previous older stars collapsing, but not forming black holes, when they collide, can generate lots of neutrons. The recoil ends up spewing out lots of neutrons, radiates things through this process, and produces lots of material in that we see in the periodic table today.
Yeah.
So combination of supernovae and neutron stars send out shockwaves and send out lots of material that's more than just a primordial hydrogen helium with traces of lithium. Anything make something before we go on?
It's not entirely related, I guess, to the question of the nucleosynthesis. But can you have a collision with neutron stars between two neutron stars that produces another neutron star, not a black hole? Like, how likely is that?
It is possible, depending on where the neutron stars within the rates of stuff, and depending on how they collide. How there's also a matter of their spin and rate of collision, how much material goes into the successor body that could result in enough a mass dense enough to form a black hole, or it could form a neutron star.
Okay. And this is a pretty active area of research. I think, like, I remember when I was very young, the general sense that I got, at least, was that it wasn't neutron star collisions. It was pretty much mostly just supernova. And we've really learned and been kind of surprised in the past decades to see how often neutron stars really collide.
Yes, and it was a problem because people were on your nuclear physicists were saying, these supernovae are pretty fantastic events, but their ability to create lots of things like platinum gold is somewhat limited. And you would have had to have exotic supernovae collapses, lots of them, to produce some of these other materials there. And it wasn't until we said, well, there's actually lots of neutron stars, and neutron stars collide more often than you otherwise would think. And that when they collide, they spray out lots of neutronium, that is neutron stuff. And that neutronium, in addition to bringing atoms of various sizes, radiates things and transmutes them, resulting in lots of material in the periodic table coming from neutron stars themselves.
And is this our full set of elemental periodic table? Is there more on here that?
This is sort of this particular table stops at uranium, in part because things beyond uranium have half-lives that are so short that they don't really figure in cosmology. So yes, you can get heavier isotopes, and no doubt those are created, but they decay so fast that they're not really part of the.
And in this context, so fast can also mean 2 million years would count as it would count as the blink of an eye, even though it's very long for us. We don't necessarily mean like microseconds or a few minutes, just not billions of years, basically.
Yeah.
And uranium, all of the elements heavier than bismuth or lead.
Yes.
I think they even found that even bismuth is actually very lightly radioactive. They all decay at some rate, but it can be billions of years long. Uranium-238 has a half-life in the billions,
Yes.
I believe.
Yes. So it means that the uranium that's found on Earth had to have been formed in some number of billion years ago. Obviously, it can go through various half-lives. But you could have a neutron star collision creating uranium, even as much as like 9-10 billion years ago, and simply there's less uranium from that collision than today.
Mm-hmm.
But if you have material, even something like plutonium that has plutonium-242, it has, I think, a 24,200 year half-life. That is so small, short of a time frame compared to cosmology, that it's really difficult to transfer plutonium. That plutonium will have decayed. And as you said, everything lead and below have stable isotopes.
Except for
Some of
43.
those things that are reactive will decay. And so if you're generating uranium and transuranic stuff in a neutron star collision, it will end up decaying and turning into into lighter material or stuff down the periodic table, including stable stuff.
Maybe a bit off-topic question. What is going on with element 43 and 61?
Those particular elements are so radioactive that
they don't have a stable element.
They don't have a stable element at all. And so if they're created, and no doubt they will be within supernovae and neutron star collision stuff, their material is so faint. And in fact, I think it was a case of was it TE43 that the estimate is on Earth, or maybe only like 2 or 3 atoms.
I don't think it's that rare.
Because though they decay, right? If something decays into it, it decays fast.
Oh, you mean at any one time, at any 1 second, there are only 2 or 3 atoms on the whole Earth that transition through this element when they go through a decay chain, basically.
Because the isotopes I thought were for this were quite.
One of them has a 4.2 million year half-life.
Okay, so obviously I'm wrong there.
Yeah, 97. So there should be. I think there are. It's 0.003 parts per trillion on Earth. A kilogram of uranium contains an estimated 1 nanogram, or about 10 trillion atoms of technetium. So, yeah, it does exist.
Okay, I stand corrected.
But it's at a low enough sort of thing that it's still clearly radioactive. Its most stable element has a half-life of 4.2 million years, which is, you wouldn't want to eat something like that. You don't want to eat uranium either, but for all I know, I don't actually know if it's the radioactivity or the heavy metal poisoning that gets you.
I believe it's the heavy metal poisoning, mostly with uranium, yeah.
Not without ketchup, at least.
And maybe they was thinking about like Francine or one of those things that there are. I know those two elements, 43 and 61, I think, were one of the last of the holes in the periodic table that was discovered. They certainly Mendeleev thought they should exist, and they were searched. They're not naturally occurring and are result of radioactive decay. So scratch that bit about a couple atoms. There's another there certainly is as another thing. Hold on a second. I'm just getting. I have. There is some storm that I've got to.
A solar storm?
No, it is a twist storm that I've got to. Somebody made a point of there's several people that are keep pinging on there, so I apologize for all those pings. I really shouldn't be presenting here. I should be doing other things. But okay, let's move on. Any other questions, comments?
No.
I have.
Maybe clicking on the screen first.
I have to hide alerts. I was getting floods of alerts from this thing, so I was unable to click on it. Sorry. All right, back to here. So let's talk about planetary system formation and nebular hypothesis. Who wants to?
Yeah, I found this when I was making some slides, and I found that like one of the first people who proposed one of the hypotheses that we even accept today about the formation of our solar system, and also exoplanetary systems by extension, was proposed by Immanuel Kant.
Okay.
Yeah, and he proposed that they knew about nebula, but he was the first one to connect that our solar system was probably formed from those nebula that they could observe, and that would explain basically the collapse. We will go to that in the later slides. But when a nebula collapses, it collapses such that every single planet within that system will orbit in the same direction around the star, basically. Of course, we will do it in the next slides. And as the slide says here today, this is the most widely accepted explanation for planetary system formation. And you have some pretty neat pictures about a planetary nebula, the Orion Nebula, one of the most beautiful nebula in the night sky.
Now, in these nebulas, unlike previous nebulas, and our current nebulas now, there are more heavier elements, not just hydrogen and helium. At this point, we have the higher elements now in our nebulas.
They are still mostly the primordial hydrogen and helium, sprinkled with a bit of death stardust.
Yeah.
Basically.
Yeah, the vast, still the majority of it is going to be hydrogen and helium, because that's sort of the nature.
Yeah, 99% plus. Yeah. I don't know, how much of the nebula is composed of original hydrogen helium. I probably when a star goes supernova, I would still guess that stuff also still contains a lot of helium and hydrogen still, right? When a star goes...
I mean, most of the hydrogen and helium I think is original in the universe.
Yes.
It was never part, most was still never part of a star, basically.
Yes.
Or a bigger atom, because when you get the heavier elements that decay, they do put off alpha particles, which are helium nuclei. So maybe there is actually a sizable chunk, but I think it's mostly a rounding error.
Yeah. I got another message from a colleague who's screaming at me saying, that my misstatement about elements 43 and 61. The element 61, however, they said is quite rare on Earth. They're estimating only about 500 grams in Earth's crust at any one time.
Yeah.
Fairly. So they're not. Then essentially, you're not going to find them naturally. And again, if they get produced, they will decay relatively quickly, depending upon whether you're patient or you're on a cosmological scale.
Yeah.
So move on.
Yeah.
Yes.
No, real fast. Who is this guy?
Immanuel Kant,
Immanuel
famous
Kant.
physicist.
Yeah.
He's the famous philosopher.
A philosopher too. Yeah, he was also a philosopher. Like
no, he wasn't
then,
a physicist, as far as I know.
Yeah, like back then, the difference between a scientist and a philosopher were less distinct as today.
Well, it was also called so they used terms like natural philosophy back in those days.
Yeah. But go on.
Go ahead.
I was just going to say that the you've got these big gas clouds, and one of the things that I remember, I took an astrophysics class in undergrad, and the rotation rate, if you have like a giant molecular cloud and that extends like a couple of light years or something, maybe the actual rotation rate, they're very, 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 very slow. They're literally like out at some distance, if I'm remembering correctly, which I could be not. They're rotating at like the tangential velocity is on the order of centimeters per second.
Yes.
It's incredibly tiny. Like an entire rotation would take like many billions of years. They don't. It's sort of in that sense.
Yeah. Of course,
millions of years. In millions of years, they slowly rotate, but I think it is on a millions of year scale.
Yeah. Well, because then when they collapse, you get the ballerina effect, right? And it goes much faster and faster and faster because a very small rotation rate when you have an extremely large body or cloud it still has an enormous amount of angular momentum because it's just got this enormously long lever arm. And so basically any amount of rotation is going to necessarily result in rapidly rotating smaller objects.
It's also important to note that like in the cloud, you have different particles moving in a different direction. Like some particle may move in this direction, and some particle or gas, dust, dust particle, whatever, may move in another direction. But the point is that if you add up the momentum of each of these particles, the sum of angular momentum is not zero. Like if it has to be like in order for it to be there is no such thing as a perfection. Any non-zero angular momentum, as you said yourself, any non-zero angular momentum means that when it collapses, it will amplify that spin basically, and eventually produce a accretion disk, because things perpendicular to the angular momentum cancel each other out. They will fall into the star. But things that rotate with the angular momentum don't cancel each other out. So they will keep orbiting around the star. And that's how you get disk.
Yeah. And I think that's a good point because the collapse is not simply it just piles in to form a black hole and everything's gone, right? You get a star formation, but you also have material that has enough angular momentum that doesn't spiral down into where the star is going to form. And this is where your planetary system is going to form. Remember also, the reason why this thing is collapsing in the first place is because some other supernovae or event has sent a shockwave through the gas cloud, and that shockwave has collapsed, has pushed material together, and began a
runaway.
densification, right? A lump.
Does it also? I would imagine that it also changed the angular momentum of the gas cloud itself too.
Well, it's imparting a force, so it will
Yeah.
it will have a
Yeah, like does the magnitude of angular momentum also affect the solar system formation? Like, if obviously if the angular momentum just happens to be perfectly zero, which is almost like I don't think it's ever the case, then everything would collapse into the star basically. But of course, if you have faster angular momentum, maybe you have more planets. I'm not sure.
I don't know that there is a well understood connection between the amount of sort of angular momentum and the in the giant molecular cloud that collapses and the number of planets. Generally, giant molecular clouds form multiple stars.
Yeah.
I think.
yes, that's correct.
Yeah. Like the beautiful picture that we saw of the Orion Nebula. I mean, it's also, I mean, it's a giant cloud of stuff, and parts of that are going to can collapse and form things there. Like that whole thing isn't necessarily, maybe it is, I don't know. But locally, it's all going to be sort of turbulent.
Yes.
Yeah.
And you'll inside there are many stars that are in process of have formed and are in process of forming. Because the and giving a scale of stuff, it is a fairly large object, and the radius of the main Orion Nebula is about 12 light years across. For the dense material, it's not the you're seeing in there. It's the dense bright part, which is the nebula. The rest are streaming out. That's a little bit farther away from it. And so there certainly are lots of protostars being generated down inside the core of the Orion Nebula as they're taking birth.
Indeed. So, but when they start collapsing, though, it's interesting because they don't. Initially, the cloud is supported sort of in hydrostatic equilibrium. The pressure just of the gas supports it from collapse. But when you compress it to a little bit more, you perturb it just enough, then the gravitational force is stronger than the pressure, and it collapses, and it collapses almost in like a free fall fashion, if I recall.
Yes. It's a snowball effect. It starts to contract more. Gravity gets stronger, and the gravity gets stronger faster than the temperature will trying to inflate it back. It cannot stop it from collapsing. Basically,
and it's also radiating.
Yeah. One thing we can also mention, like can you go back one slide? For a few seconds. Previous slide, yes. Like in the last sentence, I put there that this collapse explains why everything in the solar system's orbits in the same direction. But it also explains why most planets are also rotating with the same angular momentum, except that there are a few exceptions. Like I think Venus rotates very slowly in the opposite direction, basically, probably due to a collision during the formation.
Yeah. And so in this process here, certainly Kant, in his 1755 publication, hypothesized this might be happening, and gave some vague guess things as to why it's plausible. But as we began to better understand formation of nebula and star formation, and then had better observations than what was available in the mid 1700s. We now have that process has now elevated up, and we're now reasonably certain about planetary system formation because we have lots of examples of it. So it has elevated stuff. So let's move on to talking about the planetary system formation, right?
These are a few examples of observed protoplanetary disks.
Yeah, where it was just a concept. Now we actually have observational things backing up this process.
And there are many, many more. Like I found like dozens, if not hundreds, of images out there, and these are the two that I found pretty clearly. Like in the left, the same nebula that you previously saw, the Orion Nebula.
Yes. Yeah. And there you'll see those nodules, those knots that are in process of forming planetary systems. And as you mentioned, the angular momentum of things, things that have enough angular velocity that they don't collapse into the star, is where where planetary disks can form. And again, as I said, it's sort of a disk of loose material that's only going to go further process.
And on the right, you can even see like rings on the planetary disk. This probably means that there is like a forming planet within those dark bands that are gobbling up the material. Probably.
Yes.
Yeah.
Yes.
That's exactly what it means.
Okay, move on to the next one here. So as I say, the formations of planetary systems is wide and quite wide and quite varied. I think probably the thing that's happened in maybe the last half century of planetary science is we've gone from a notion that perhaps planets are rare to now knowing that planets are quite common. And in fact, given the mapping of planetary systems within, let's say, the first 1,000 light years or so, which is typically sort of that pushes the limit in terms of being able to easily detect a planet. We, based upon that volume of stars, we know now that stars greatly outnumber planets. Assuming that this volume that we're in is typical, we know that our galaxy of around 200 billion stars contains at least 1 trillion planets. There's at least five planets for every star. Not that every star has planets, but that's a population ratio.
And it's also notable to mention that the most common planet, I think that's one slide later actually to also show.
Okay,
see, the most common planet that we find are super Earths, rocky planets that are like larger than our own planet. But of course, that doesn't mean that they are habitable. Most are probably not habitable.
Well, that's not quite okay. We're jumping ahead, and that's not quite correct. But
all right.
But we'll get there. So the point is that this table shows a thing for some of the graphical representation of some of the planetary systems that a mission called Kepler found, that they came in a wide variety of shapes and sizes, distances from their parent stars, and of what we've detected. And again, the key thing is what we detect. If we move on to talking about what we detect, this next graph, come on, there it is.
That's the graph. Yes.
Shows you what we've detected. The problem is that it's very difficult to detect small, low mass planets.
Oh yeah, there may be a bias there. Like we're probably missing a large fraction of smaller planets. So maybe smaller planets are a lot more common than we think.
Yeah.
And so while there are simulations that suggest that's the case, it's probable that rocky dwarf planets and icy dwarf planets are probably the most common object out there. But the simulations and observations tend to agree. But it's likely that as we get better detection, we will find that the terrestrial planets will come up in proportion to the super Earths, and then the dwarf planets will come up in proportion to Earth planets. But that remains to be seen. Any other comments?
This graph here, exoplanet size in Earth radius, is Neptune only 4 times bigger than Earth?
It is relatively compact. Neptune is actually, although it's more massive than Uranus, it is a fairly compact size.
I didn't realize they were that small.
I mean, Neptune's radius, you're talking about its equatorial radius, is about 3.8 to 3.9, about 3.9 Earths.
Wow.
But its mass is around 17.2 Earths. So it's a lot more massive.
We might be getting to this later in the slides, I forget, but is there a reason, are we talking about reason why the more gassy planets are on the outside and the rocky planets are on the inside?
We will get to that, yes.
Okay.
So let's move on to the next thing here. And we're going to talk about the formation of our solar system, which, remember, started with a lot of hydrogen and a fair amount of helium and some lithium present. Come on, move forward. So that's material, the gas out there. But then some heavier elements came from supernovae and neutron star collisions that got impugned into the gas cloud, and due to gravity, they collected the matter that wasn't in the sun was collected into pebble-sized and boulder-sized chunks. So you got low gravitational accretion. We're talking about material that didn't go into the star, has enough angular momentum to stay out of the star.
Yes.
And then those small boulders accrete to form planetesimals of a few kilometers in size, as they essentially create these sort of rolling dust bodies, gathering up material in their orbital zone. And over some period of time, probably in the several 100,000 years, those planetesimals run into each other, collapse, and deform into sort of spherical sized objects, which are the planets, starting off with dwarf planets and accreting up from there.
And this image is a very good image to show all of the planets and also many of the moons and dwarf planets. Like Ceres is very tiny there. And you can also see that the Earth is about 1/4 the size of the gas, the ice giants. Yeah. But Jupiter and Saturn are obviously much bigger. But of course, this image shows you how they compare in terms of size. But later we will see how their orbits compare to each other.
Yes.
Yeah. What is that little planet-sized thing between Jupiter and Saturn?
Oh, those are the moons. Those are the moon.
And so one of the things in particular you talked about, our solar system contains, this might shock people, over 110 planets as defined in the geophysical model. You might say, 110? Did you make a mistake? And the answer is no. Did not make a mistake. The geophysical definition of a planet includes an object large enough to deform itself into a spheroid that's not orbiting a fusor like a star, and in some cases, some natural satellites of a planet we call moons. But some of those larger moons are big enough to also fit the geophysical definition of a planet. So in the effectively, if you say in our solar system, round things, circle round things that are not fusing elements, right? So again, geophysical definition. They're large enough to deform into a spheroid,
Yeah,
and they're not fusing elements
its
like
internal, its internal gravity is strong enough to compress it down into a sphere.
Yeah, but they are not fusing elements. Let me be clear. They're not a fuser. They're not fusing elements to form a star. Like a fuser does, right? So they're large enough to deform themselves into a spheroid, not fusing elements, and orbiting within our solar system. You have an object like Ceres, which was called, our planet is now called a dwarf planet, because it's round enough to have to form to basically be in a ball shape.
And Ceres is in the middle of the asteroid belt.
Yeah, Ceres is one of the dwarf planets in the asteroid belt. So Pluto is a dwarf planet, and it orbits out mostly beyond Neptune, although it crosses a little bit inside it at times, and as well as Charon, as well as our moon is a dwarf planet. Io, Ganymede, Callisto, those things. Now the small rocky bits around, that those Phobos and Deimos, those two sort of believed to be captured asteroids orbiting Mars, are not dwarf planets. They are not big enough to have warped themselves into a spheroid. So
they look like asteroids, like they have like elongated shapes. They look like the classical asteroid. Yeah.
So again, if it's big enough to form itself in a spheroid and it's not fusing elements, that is not a fuser, it can meet the geophysical definition. So people want to ask, is Pluto a planet? The answer is yes, Pluto is a planet. What type of planet? Is a dwarf planet. And you say, well, I thought I heard IU, blah, blah, blah. No, the people that planetary science has come up with this definition, and the definition is not based on where it is, but what it is. And so Pluto is a dwarf planet. What do you mean dwarf planet? Dwarf is a type of planet.
I also found the NASA definition very convoluted. Like, according to that definition, Jupiter is currently a planet, but if you throw it out of the solar system, it no longer becomes a planet anymore because it doesn't have an orbit anymore. But nothing about Jupiter changes. Yeah, it's very weird.
So that's why the geophysical definition is as adopted by planetary scientists. Talk about properties of planets. So if a planet is ejected from its planetary of its solar system, then it becomes what's called a rogue planet, right? Mm-hmm. So these are modifiers, right? That just like dwarf stars are stars, and dwarf galaxies are galaxies, dwarf planets are planets. Pluto is a dwarf planet. Ceres is a dwarf planet. Our moon is a dwarf planet. Io is a dwarf planet. That's and when you start adding up all those objects, you end up with something like over 110 objects in our solar system that qualify as a dwarf planet. Okay, moving on.
Where does the term wandering planet come from? I thought it was wandering stars. That stars were called wandering planets.
Yeah. That's the original term for planet. It was like how do you call it? Asteros planet. I don't know what the original phrase was in Latin, but or Greek. I don't know. Yeah, the phrase meant wandering star, and then the word wandering was basically planet, and then we kept the word wanderer as a name for those objects.
Was that was back when we thought we were the center of the universe?
Yeah. We looked in the sky and we saw stars, and the stars that didn't move, they were fixed stars, and the stars that did move were wandering stars, and those are the planets. Yeah.
Sure.
Yeah.
So this figure shows that these objects within solar systems orbit at different rates, different distances. There's Kepler's law of motion, talking about the relationship between the speed at which it goes around the parent body and its distance. Right, there's a nice Kepler relationship. This talks about some of the larger planets there. Obviously, it misses a lot of the dwarf planets. Because if you put in all the dwarf planets, the slide gets quite busy.
Yeah. Like it shows the scale of the orbits to the proportional.
Yeah.
Mm-hmm.
So the sun and his birth things you want to talk about this, the birth cluster.
Oh yeah, yes. Like again, another beautiful example of a nebula, or in this case, it's often been called a stellar nursery because it's a very active place where new stars form, the pillars of creation. And look at another beautiful image that we get from, I believe it's another Hubble image, right? That one.
Yes.
Mhm.
Now there's a massive star that's not in the frame but above the frame, whose radiation pressure is stripping away the gas material. Gas material is already collapsed down into, in other places, into these little nodules, these protoplanetary and protostar systems, and they are in the process of accreting, and material is falling into the center, to the process of beginning to create a star, as well as the material that's orbiting around that center is in the process of forming those planetesimals.
Yeah. Also, one thing that this slide wants to convey is that there is, like, we find the decay products of I believe aluminium 26 and iron 60, and these decay products or these elements are very rare, and they are only produced by stars that go supernova, and they decay very quickly. So what this suggests is that our star, like our solar system, was born in a stellar nursery that contained hundreds or thousands of other stars in the same stellar nursery.
But-
And the reason why we think this is because supernova are fairly rare, like 1 in a few hundred go supernova. So in order for the odds to add up, is that our solar system had to also have been present within the same environment as the supernova as well.
So, is there any particular reason why we named the planets after the Roman gods?
We didn't. The people who worship those gods did.
Yeah, it's
Yeah.
traditions. So back, say, with the business of the you're talking about of stars, the stellar nurseries kind of come in various shapes and sizes, and depending on the shape and size and the shock waves that hit it, you can have the nursery becoming completely developed in forming stars, or you can get stars forming, let's say, on the edge of a nebula, and those stars in turn, the birth of the stars can create further shock waves. So I mentioned that supernovae are important in the beginning collapse of gas clouds. Another process that once stars start forming in a nebula is other stars. So in this particular object here, the object that's sitting there on the left, the pillars of creation, there's a much more massive star above whose light pressure is causing further collapse of that gas cloud. So an additional factor that comes into play is stars, their birth. But basically, when the stars sort of quote switch on, they push out, the radiation pushes out, in addition causing further collapse around it that can form other planetary systems and other stellar systems.
Yeah, I think that the picture on the right there showed that like makes it very clear that tail there is it's sort of like the star is almost acting like a comet.
Yeah.
Like it's the same effect that creates a comet's tail. And yeah, it's really cool. What are these other things? Are these all other just like stars, presumably?
There are,
I think so. Yeah.
I don't know where
Yeah.
that picture was. I don't familiar with that particular object area, but those are probably proto stars.
That's the same. That's H.L. Tauri. That's the same. So I think the one of these stars might be the disk that you showed earlier.
Yeah,
Okay.
I think it's the same. It's the same object, but a different image. Yes.
Yeah.
This is also another interesting thing that I found. So it has been suggested that the collapse, like as you mentioned before, that neighboring stars, when they form or die, like when they die into supernovae, or if when they are born, they push out against the surrounding gas. So it has been suggested that the collapse of our solar system has been triggered by one of those shock waves, either a shock wave of a supernova or the wind produced by the birth of another star.
Or a combination of the two.
Or a combination of those, yeah.
Yeah, and also neutron star collisions also have a factor on that. There are other things. You can have active galactic nuclei with a massive black hole that's active, sending out jets. So those are also some of the processes that can form to cause collapse. One next. So
also in the previous slide you saw. Okay, sorry about that. In the previous slide you see this the totem, which is basically a god from the Aztec tribe that is the mother of the sun, basically. In this, and the hypothesis that our solar system collapsed due to a shock wave or something from another star, it refers to that hypothesis, to the name of that deity. Yes.
So in our solar system, we were certainly affected by a neutron star merger. Because again, you look at the periodic table of elements and you look at what we find on Earth and elsewhere in our solar system, we find a lot of material that was actually, rocky material and other elements that came from a neutron star merger or mergers. Could be certainly more than one.
It's almost like a domino effect type thing.
Yeah. Okay. Next.
And this is another like as mentioned before, like our sun was probably one of many sisters, hundreds or thousands forming within the same stellar nursery. But since our formation, we have drifted apart, and we don't know which star are our sisters, because they drifted in different directions and they orbit the galaxy.
So within so our sun almost certainly formed in a stellar nursery of multiple stars. Since the sun has formed, we have probably traveled around. We've orbited the galaxy probably at least 20 times, if not more. And what we know is that if there are, if we could find other stars that came from that same gas cloud that our sun formed in, we're likely to find similar element materials, right? The elements that got stuck into there from the point of view of supernovae and neutron star collisions, they probably have a similar element mix. They certainly would have a similar age to our sun. And if things progress like they do, they might have similar interesting planets. So this notion of finding the siblings of our sun has been a thing going on for quite some time, for quite interest, but it became somewhat practical to start to search for it through to a mission called Gaia, which was a European Space Agency mapping that tends to map about 1% of luminous objects in our galaxy, get a notion of how our galaxy is actually forming by measuring very accurately position and velocity of stars in our galaxy, to try and as well as classifying lots of objects. There'll be other surveys, like, for example, other telescope surveys that will try to classify and find stars of similar ages with similar isotope mixes that might also be the siblings of our sun.
So like almost like a DNA test to see which ones are brothers and sisters stars.
Yeah, in some ways. So moving on again, you tend to have a distribution of material when the star switches on, when fusion begins in earnest in the center mass. The radiation pressure pushes material out. Now, that material that's gravitationally bound forms a star, but things beyond the star get pushed out. Basically, it pops. It feels almost like it pops a bubble in the planetary disk of the lighter gases. So the hydrogen helium gets pushed out far, and then beyond that, the star's ability to heat stuff diminishes, and so you get what's called a frost line. So you have an central region that's been evacuated around the star, and the frost line. Now, in the case of our planetary system, Jupiter is that bubble, right? If you think about the sun switching on, the pressure pushing out material, and it was able to more effectively push out hydrogen and helium. The bubble it popped, the edge of that bubble became Jupiter.
And that's why Jupiter is so
left
massive.
Inside that's left inside is more of the heavier materials that form the rocky planets of Mercury, Venus, Earth, and Mars. By the time when Jupiter formed at the edge of the bubble, right, its mass was sufficient that it began to accrete and pull in material from the asteroid belt. And as a result, the asteroid belt was only able to form one planet, Ceres, the dwarf planet, and the rest were just too small to be able to accrete to form anything of any particular size. So Jupiter kind of ripped off the material that could have been forming a planet at the asteroid belt. It even did effectively stealing a lot of material from Mars, so that Mars is also rather anemic in its density and mass.
And I believe Jupiter also causes the asteroid belt to not be able to coalesce into one object, right? So that's it keeps the asteroids dispersed from each other.
Well, there's not enough material to be able to accrete. It was too thin to be able to do the accretion. But even in the case of Mars, excuse me, Mars is only about 1/10 the mass of the Earth, and it's a fairly light as far as rocky planets go.
In terms of density, how dense is it?
I mean,
compared to Earth,
its density is, I think that the density set is, I forget, compared with Earth. Where the mean density is around 4 grams, 3.9 grams, if I recall, per cubic centimeter, as opposed to Earth's. So the mass of Mars is about 1/10 the Earth. Oh. Its radius is about 0.5, about a little over half the size radius of the Earth. So it's got a lot more volume. It's got 15% of the 15% of the Earth's volume and 10% of the mass.
Right. Is that the same reason why the Kuiper belt didn't coalesce together?
I mean, again, it's a matter of you did not have a dominant object that began vacuum up the planetesimals.
If you have a large enough object in the vicinity, then everything will eventually collapse into that object, basically. Yeah.
Remember again that matter began in the early part of a planetary stellar system, starts collecting sort of pebble-sized, bowl-sized chunks. And those chunks accrete to form planetesimals a few kilometers in size. And those planetesimals then begin to collide and coalesce to over a period of several 100,000 years to get enough mass to form an object. And so when you have an area that's relatively thin, your pebbles aren't going to be able to accrete very fast, and even the planetesimals are thin enough that they're not going to coalesce to form a planet.
Okay, what's the difference between how do they? I don't say decide, but that's a bad word for it. But to either accrete together or to just to orbit each other.
I think we will go into the later slides that well. Yeah, we will go into that.
Okay. All right, next.
This is like more details about the frost lines. Actually, you have several frost lines. Like you have one line where rocks can exist, and then beyond the one you have the snow line where ice can form, and then further out you have also a carbon monoxide line where like even more volatiles like ammonium and such can condense.
Yeah, so if you see this thing here for our system, we had material where that snow line is way out in the Kuiper belt, but we have a particular a accumulation line a little beyond the asteroid belt of some of the lighter material, but again, Jupiter then kept forming and ripped off and sucked in material from that. That wasn't able to accrete very, very effectively.
And it also explains like a dichotomy that we observe among the asteroids. Like asteroids are mainly two different types: the NC types and the CC types. The NC types are non-chondritic, and the CC types are chondritic meteorites. The chondritic basically means they contain more carbonaceous, and they are also often a lot more wetter, and the non-carbonaceous are more drier materials. And you can also see among the non-carbonaceous meteorites, you also see differentiation. Some are iron, like very highly rich in iron, and some are very depleted in iron. And these indicate that they were once part of a planetoid where some material, so like the iron was sinking down inwards, but then later on these planetoids were ripped apart, and that's why
some of these objects, however, are primordial, right? So not every body out there is there. Now a lot of meteorites and meteors that reach the Earth are there's a bunch of them that gets formed when asteroids collide and shatter and pieces fly off. But there's a number of them also that are primordial, that are essentially those original chunks that never got into a planetesimal, or planetesimals collide and pieces of them fly off and form those small chunks again.
Yeah, the pristine meteorites are probably the chondritic ones. They're also among the oldest objects, basically. Yes. You can also see in the image on the right top. Yeah, in the previous slide on the right top. Yeah.
All right. So next.
This is on slides showing some of the mechanisms of accretion. Like first, you start with dust grains that stick together basically by electric molecular forces, like van der Waals forces, or maybe electrostatic forces that will clump small grains together. And I think we also observed, like there's one famous video of people in the ISS. They put basically sugar or coffee mixed in a bag, a plastic bag, and they shaked it. They shaked the bag, and then when they stopped, you saw these grains of sugar and coffee grains sticking together, basically on the ISS.
Sure.
Yeah.
And that also is going to be affected by them being in I think generally speaking, a fairly thin gas at best. Dust grains behave differently under vacuum compared to.
Yeah, also, yes.
Okay.
And I will, sorry, but there's one more slide one more thing to note in the previous slide. Sorry about that. Like those molecular forces get you up to about 1 millimeter of grains, but then to concentrate them enough, you need to concentrate those things enough for them to collapse even further into mountain-sized objects, and that is the next slide. So sorry, yeah, that's the next slide that will go into that. Mm-hmm.
Okay, so that's...
We're on the nenext slide.
All right. Let's see here. I think we also covered this before, but beyond the snow line, you have a lot more material, basically, right, to accrete around. So
yeah, but I think it's specifically saying that it's literally like collecting like frost, and
also yeah.
And so like when an atom actually hits it, it'll stick because it'll freeze, and that is because I know there is a question. It's not entirely well understood, is my understanding. How you go from sort of boulder-sized things to sort of at some point it becomes difficult because the collisions are have a tendency to destroy everything before you just figure out point.
Like, do we know
this would help explain that to me at least.
Do we know how massive or it has to be before it starts going into a more spear-shaped form?
It depends upon the material, right? If you have a fairly iron-rich material that's very dense, its ability to deform is very different than if you have a gas.
Yes.
Right.
Yeah, certainly. Yeah, I was going to say for turning spherical, they have to be like decently chunky, I think.
So,
yes. The other day, sorry, if you want to say something like
no, go ahead.
All right, this basically explains why the gas giants are so big. I've seen one source that says that each planet probably started out as a rocky core, but in the outer, beyond the snow line, where you have a lot more gas and a lot more ice to accrete, they grow a lot faster. And when these rocky cores become about 20 times Earth masses, then they have enough gravity to capture the hydrogen and helium, basically. And at first, this capture is a bit slow, but when they captured enough of this hydrogen and helium, then they become more massive enough such that it becomes a snowball effect, where when the accretion becomes so fast that they will reach their current size in a few thousand years or so. Sure. Yeah.
It also helps the fact that a lot of material in a proto-star protoplanetary system is hydrogen and helium, right? Remember that when the star, the fusor switches on and and the radiation better pushes out, is going to be more effectively pushing out the hydrogen, helium, the lighter elements, and the edge at which it be able to push out, where that pressure where it slows down, is where you'll get a gas giant forming. That gas giant has lots of mass available to it, and so it's there. Although you'll see in this thing, gas giants do have cores. And in the case of Jupiter, is even more complex because some of the core is weird stuff like metallic hydrogen and other things. But there is rocky stuff in the center of these gas giants as well. They just have able to vacuum up the most of the mass in a solar system, which is hydrogen and helium. But you can see down there, there's metallic hydrogen and other weird stuff, and there's liquid helium down there and other weird things happening.
Yeah, and I believe metallic hydrogen is probably the reason why Jupiter and Saturn have like very powerful magnetic fields.
As well as the weird things happening with super fluid under high pressure helium and other things like that going on. Let's move on to the next one.
One last thing is that the ice giants like Uranus and Neptune, they captured they basically lost the race to become giant, basically. But they captured they are left with a disproportional amount of the other ices like ammonia and methane. So they have a slightly different composition compared to Saturn and Jupiter. And that's the final note on this slide. Yeah. All right. This is basically the slide that answers your question about like how do objects become more massive, basically, right? They start to migrate and accrete more material as they move through the dust, and that causes them to migrate around. Like I found this image or these images on a website run by Sean Raymond, I believe. Sean Raymond.
Okay.
Yeah, this is so planets like Neptune and Uranus, they probably didn't form quite as far out as they are now spotted. So they had to sort of migrate, and the planetary migration, it's a very sort of rich topic, and it can actually go in a lot of different ways.
Yeah. So let's move on to this one here. Talk about planetary migration.
Yeah. So basically the core story of how planetary migration is happening is it's all about the exchange of angular momentum. You have a body that is interacting gravitationally with the dust and the gas all around it, and the thing about it is that all of that is in a Keplerian orbit, and it's differential, which is why the stuff that's going inside sort of passes it and gets slowed down, and the planet ends up going faster. And that can make it go inward or outward. Both the sort of type 1 migration, which is what it happens when the planet is sort of a small perturbation on the disk, that happens generally inward, but it depends on the sort of density profile of these disks.
Yes.
When and at that point, the planet isn't really able to carve out a big gap. Like we saw in the previous slide that you just sort of saw it was a little bit brighter, but it wasn't making a big like donut that we see in
Can we go back one slide just to see those images? Yeah. We can explain the different types of migration better that way.
Yeah. Yes. In type 1, generally it's going to go in, and but it's not able to clear out. There's not a big clear donut. The darker areas are where it's less dense, and the bright areas are where it's more dense. But as it gets larger, it transitions to type 2 migration, and then it's really clearing all of that out, and it's sort of like how close and how far the planet is from those bands of gas that sort of define those edges. And it's sending all of these spiral density waves out. This is a very similar type of physics to what causes certain types of spiral density waves in galaxies. And you'll have multiple of these planets interacting with each other, which eventually is going to cause also just straight up gravitational scattering off of each other. And in the transition from when it can't carve out a deep gap to when it is able to carve out a deep gap, that's when it really accretes a lot of stuff, and it can actually migrate on the order of just like 1,000 or 10,000 years. It can migrate dramatically, and have the orbits change.
Yeah. Let's move 2 slides ahead to this
there's also
one here. Let's go to this one here.
But in the previous slide, there's also the tag. I don't know if you want to cover the tag model, or do you want to skip the tag model in the previous slide?
I'm not familiar with it.
Okay, can you go back one slide? No, this one, yes. Although the text is a bit warped, I apologize for that. But I found the grand tag model which proposes that Jupiter formed early. Around 3.5 Earth orbits away, and it migrated inwards. As you said before, that type 1 migration is most often inwards.
Mm-hmm.
But when Saturn later catches up to Jupiter, then Jupiter and Saturn started to interact in such a way that both started to migrate outwards to the current position. And this is called the tag model, where first the giants went inward slightly, and then later they moved outward to the current position. All right. And this is the NICE model. Not the nice model, the NICE model.
Or the nephew model.
Yeah. So yes, and that sort of talks about the fact that Neptune and Uranus switch places given.
Yeah.
Yeah.
Like I believe this model was first proposed to explain what's called the late heavy bombardment, like about 4 billion years ago, like 500 million years after the Earth formed. There was a late heavy bombardment where a lot of impacts were happening on Earth, and this model was proposed to explain that event. But now I believe now we think that this event was unrelated to the late heavy bombardment. I believe so.
Okay.
Yeah.
So we're going to switch over and move over and talk about what might have been the early Earth, because Earth is one of those rocky planetesimals that formed, and okay, we use this as a thing. So remember that there's a number of rocky planetesimals accreted within Earth's orbital zone. Early Earth was probably largely in a molten state due to the heat generated from all those collisions, right? The merges there's lots of heat that gets formed from the things hitting together. And after most of the planetesimals in Earth's zone merged to form Earth began to cool, a crust began to form. And there were sort of final rounds of collisions that formed larger craters, and cooling released large quantities of gas, because things outgassing, and water that was trapped into the cooling rock, right? So it began to accrete out there. And then early supervolcanoes further released that into gas and water vapor into the atmosphere that was gravitationally bound. Began to get a fairly thin atmosphere. Icy bodies continued to impact the Earth, stuff from outside migrating inward. So some of the water, and an open question of how much was delivered to Earth from icy bodies farther out, comets. Some of the water obviously formed in where Earth formed, right? So Earth had some water in it. Some other water was delivered to it. And so the combination of the water delivering Earth and the water that formed Earth is what Earth has today. The Earth continues to cool, and the oceans begin to form.
Mm-hmm.
This is very, very, very early Earth.
So this is what the geologists call the Hadrian period or eon.
Oh, this is even before the Hadean. Like the Hadean was after the moon forming impact. This is just before. Like now we are still before the moon forming impact. Yes.
Okay.
Okay.
So we're going to go over to here. Let me move on to this thing where, so early on in Earth, so in this early Earth thing, the Earth was impacted by a very large planet called Theia. The estimate of the mass is around 6,100 kilometers in diameter. It's about the mass, and had about the mass of Mars. The collision vaporized a lot of Earth and Theia. The energy of the collision caused a lot of the material to vaporize. Debris was ejected into space, but was still gravity bound because it wasn't going fast enough to basically achieve escape velocity and keep going. Debris accreted to form. Certainly, a lot of material fell back into Earth, but some of it also began to accrete out at the next zone. Just like planetary disks form, you had sort of a zone form around this sort of molten Earth, and that's where the moon began to form. Debate about whether it was a few million years or just a few years of forming the moon is still being debated. There's different models that suggest one or the other.
And Theia was the last object in our way till we were the dominant form in our orbit path.
Do we know whether Theia came from outside or inside?
We don't know whether Theia was a planetesimal that was late accreting, or it was something that had elliptical orbits due to some, because one plausible model is that when Jupiter and Saturn were doing their dance and help causing Uranus and Neptune to shift, there likely was some body out there that got tossed inward.
Yeah, because we also have to explain, I think, the backwards rotation of Venus, for example, because in this entire process, generally speaking, there's a tendency to just keep sort of rotating in the same way. And as we mentioned, Venus actually does rotate slightly the opposite.
And I believe also Uranus also has a very tilted axis, like almost on its side, basically, which is probably also due to an impact event as well. Yeah. In order to change your angular momentum, you have to exchange it somehow, and impacts are the main mechanisms to do that. And I believe also in the beginning, we can also discuss it later on, is when after the moon forming impact, the Earth rotated very fast, like about one rotation.
Yeah, but we're getting ahead of ourselves.
Sorry about that. Yeah.
So. Hold on a second. I'm getting audio noise here, and I don't know where the audio stuff is coming from.
Okay, did you open up the link? I think you want to show the animation, right? So maybe that's the audio from the the animation you want to show.
Okay. All right. So let me do this. So sorry, this is a fairly obnoxious presentation process. So what I need to do, because I can't participate and get this stuff under control at the same time. So you had to keep talking and get ready to do a presentation, or just.
We do have a question from the chat. Like, could Theia have been a Kuiper belt object that got flung inwards? Like, I'm not sure. My gut feeling is no. That's just my gut feeling. Because you're muted, Tapio.
Yeah, I would say that it probably wasn't, but it could be. We don't know exactly what it was. We know more about its composition, I think, than we know about where it came from. It just seems very plausible that it was another planet or planetesimal.
Yeah, I think it's more probably the case it would also be another rocky planetesimal in the neighborhood of Mars, Venus, and Earth, probably, right? That
Yeah.
would be my
So
guess.
this side
Yeah.
of the asteroid belt, not the other side.
Yeah,
Yeah,
I don't know
yeah.
if there's I don't know if there's enough ice for it to be. Like I don't know if Earth has enough water for it to be a very icy body.
Yeah, it's like if it came from the Kuiper belt, like Earth would have probably ended up with a lot more water, and Earth is it's actually pretty dry compared to its own mass. Like it's a very small amount of water that Earth has compared to the total mass, of course. Yeah.
Right. Now, thinking of the Kuiper belt and stuff, is currently is what we call the Oort cloud the border of our solar system, the very edge.
Yeah, our understanding of the Oort cloud, I think, is slim because it's very, very hard to see things out there. It's they're small and very, very dim. But you do like the gravitational influence of the sun extends to like it can matter for dynamics of stuff all the way to like a good chunk of the distance to another star, like over a light year. It's very it gets weaker and weaker, but it does have some influence. I think that the Oort cloud at its very sort of largest extent is might be even have tidal effects from other stars and things like that. But I don't know how well we actually know that the Oort cloud, like as a collection of particles and dust, I don't know how much we actually understand about it.
Yeah, it's less. We know a lot less about it than there. I'm going to show you some simulations.
Can you make that full screen?
Probably yes.
Okay.
So this is a simulation of Theia Earth collision. A lot of vaporization and molten stuff occurs.
It's a very recent simulation, yes.
And there's a blob that merged back to the Earth and impacted, and another blob that hung around that's going to become
It's like you mentioned before that like a few minutes ago you mentioned that Earth the impact could have formed an accretion disk around the Earth, but this simulation probably showed that you have these blobs, like two blobs, and one blob went downwards and another blob basically when one blob went downwards it gave the other blob a gravitational kick to stay in orbit, basically.
Similar like what we're seeing here, where essentially the dribbles come down and it forces the other material back out.
And this now we're at the time of the Hadrian.
As I believe the if I'm not mistaken, the Hadrian is defined. The start of the Hadrian is defined as the impact.
Okay.
If I believe correctly, I'm not sure if that is the official definition, but I would guess it is.
I think that there are still some people who, like astrophysicists and astronomers and whatnot, who aren't totally sold on the Theia impact. I don't personally get it. I think it has become very much a the mainstream position, but it requires a lot of computer power because you just kind of have to simulate the stuff because these systems are chaotic.
Yeah.
Do you want us to
share this thing here? I'll show you, I think, another one. This one is going to be less likely to be able to show it. But this is another thing showing you the edge on, looking down from the top, and you see the material that forms, the thing splits, collides again, gives
Yeah.
a kick to the other material. That
Yeah.
material as well begins to come in, and material from it accretes in, but the resulting counter thing is it gets ejected back out.
Yeah. And this whole orbit does not look particularly Keplerian because it's losing mass along that sort of filament that you saw.
Yes.
And it's probably necessary to keep it in orbit, right? If it wasn't losing mass, then it probably would just crash down again, basically,
Yeah.
right?
And this is if you look at here, the time is like 2 hours. This is 3 hours. This is 4 hours.
Yeah.
5 hours with the first merger, and then when it comes back down in, because it has an elliptical orbit, and begins to around hour 12 begins to pour material in, that has a recoil and it kicks out at here right around hour 16, and this is like hour 19, hour 20, 1, 22, 3, and then we're out to a day. So if you look at I guess from the other set here.
Also, I have to correct myself. I checked, and the Hadean is actually defined as the oldest rock that has been detected in meteorites. So the start of the Hadean actually preceded the impact of the moon and such. Yeah.
Yeah, I want to show you the wide angle version of this thing simulation here. Okay, so see, this is the wide orbit model, and here again you see Thea coming in. The initial collision, a lot of vaporization and mold stuff. Material. There's a larger blob that's going to come back into Earth.
And that larger blob gives the smaller blob a gravitational assist, and such that the smaller blob is able to keep orbiting around. Yeah.
And there are geologists that believe that they found that larger blob that just merged is evidence of that is seen in the Earth structure internally. That there's a gravitational anomaly.
So the proto Earth was smaller than our Earth now before Thea came along, right? It got bigger.
But the mass of Thea is probably only about 10 to 15%.
Okay.
Yeah.
Of Earth. So
like it's a lot. It's the biggest thing that ever hit us, for sure, probably. Because you can make the argument that it's still us, but the moon at the end of that whole process, the moon was left in a much closer orbit than it is now.
Yes, and the Earth is also rotating a lot faster than it is today.
Yeah, but not close enough to, as the creationists say, hit the heads of dinosaurs. Quote.
Yes.
Oh my god. I love the ones who think that some scientists thought that the asteroid came in and literally decapitated these people.
It's a very special thing. I'm having to click forward to the thing because there appears to be no way to move it to the proper spot. There it is. Okay, we're back to this thing. I'm not impressed with the technology that we're using, but
very pretty
it's what it is.
I have a question about we know the angular momentum of the Earth and the Moon after the impact. Can we figure out what the most probable direction the Theia came from, basically. Like, can we figure out whether the Theia came from outside Earth's orbit or inside Earth's orbit?
Almost
figure
certainly
out-
outside.
Yeah, probably, yeah.
It's almost
Yeah.
certainly outside.
I think, that's because it had to. The Earth-Moon system has anomalously high angular momentum.
Yeah.
And that is way better explained by a collision from outside sort of coming in.
Yes, and there's a nice. This is a different style of stuff of in Wikipedia here that I think that shows essentially that it probably came. It could have had material that was sitting at what's called L4, about 60 or L5, 60 degrees either forward or backwards from Earth, and due to perturbations of Venus, cause that material to move towards Earth, so that Earth and Theia could have been orbiting around a similar path, but Theia was stuff that's accreted either 60 degrees ahead of or behind Earth, and due to perturbations from Venus, that body moved closer to where Earth was, and he ended up getting a collision.
Was there a high or low probability that this collision could have just shattered us instead of like merging?
Oh yeah, I think we could have ended up as an asteroid belt, right? But there's one possibility of this if it was like a head-on collision.
I don't know if that would.
Yeah, I mean, I don't think so, because I think it would eventually would accrete back there.
Really? It's not possible for them to just obliterate each other. Like
not with the mass imbalance. The mass imbalance was probably on the order of like 6-1 to 10-1. I don't know. I'm not.
So if the collision was more head on, then we were basically a super Earth without a moon, basically.
Well, you still would have gotten an ejecta, I think. You might get more ejecta. It could be that the mass would end up smaller. I'm less sure about that.
So this is a model showing where the object Theia came from L4, and due to perturbations of like Venus, it could have essentially wandered in towards Earth. So you see there it goes, gets in close. So they're moving around the sun, right? So you're
actually the reference frame is fixed on Earth, so the Earth is of course still moving. Yeah.
Yes. And so that's the Earth Moon forming there. So that's what we're talking about with that. That's that. So back to. I'll stop sharing. So
we do have a question. Yes. What was Theia theorized to be made of? I think if the model that you just showed is correct, then it will probably be similar composition as Earth, because it is forming in the same neighborhood, probably.
And even more similar to the moon, since actually, I don't know. Maybe the moon is formed out of a slurry that was like roughly 50-50.
If is the moon not deplete in iron? Like it does have iron, but a lot less iron, relatively speaking, compared to the Earth, right? I'm not sure.
I'm looking for material here.
I'm also not sure about that. One of the difficulties is despite how well we understand like gravity, we can't just play the movie back, like play all the planets going backwards and figure out everything that happened, because it's a lot of different interactions, and it's a chaotic system. The slightest imbalance in what you know now will eventually propagate to be a complete. You don't know what side of the sun the planet is on, and so you can only calculate backward and forward a finite number of years, and it's enough to do things like predict solar eclipses, but I don't think it's enough to do things like predict solar eclipses in 2 million years.
Oh yeah, I looked it up, and it turns out that like the Earth has an iron core which is about 50% of Earth's total diameter, and the Moon's iron core is about 20% of its
Yeah.
total diameter. So it's a
So,
relatively speaking, the Moon has a lot less iron compared
so
to its own
I
mass.
have,
Yeah.
yes, I have in my notes that there. So the Earth's moon is rich in silicates and poor in iron. And much of the models suggest that much of the mantle of Earth's moon much of the moon came from Earth's mantle. It certainly is affected by the collision of Theia, and that it explains this. By the way, this explanation is also explaining things like. In fact, I think it's probably it. Where are we back onto here? We got to get.
So
It's very difficult for me
sorry. Sorry.
to talk and try to find. Okay, yeah. So this collision explains things like the Earth's current axial tilt and the 23.5 degree tilt from orbit, the moon's 5 degree tilt from Earth's plane. But it says here that the moon was able to cool a lot faster after the collision, right? The rocky crust and craters formed soon afterwards. It was smaller. It didn't have as much of the thermal collision, so it was able to cool faster. A lot of the Maria, that's a plural of the dark patches of the moon, were formed from some of the larger collisions early on in the moon's history. But the moon didn't have enough mass to hold atmosphere, and without a core, it didn't have able to generate a magnetic dynamo. So without that aspect, there's no weathering on the moon like you do on Earth.
And this is also a fun fact about the Maria. That is, I believe that it's maybe Latin for seas or oceans, which basically refers to the fact that the people once believed that these dark patches on the moon were oceans.
Yeah.
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 But of course, they are not oceans.
So early on with that molten vapor blob of the Earth, you had what's called differentiation, and it has a density of material that had a big influence on what settled, right? So you have this blob that's sloshing around from this enormous collision, and we have the center tends to have much more dense materials than on the surface. So center has lots of iron.
Yeah, that's actually
iron's around 7.9 grams per cubic centimeter, whereas rock on average is around 3. We talk about rock that's at surface, right? However, inside the Earth, the iron core is actually crushed to a much bigger density. So if you look at the density of material, iron's at 7.9, rock, typically surface rock, is around 3, water's at 1, and atmosphere is like 0.0012. So this drives a lot of the structure on the Earth from this molten system. So we no longer had this dust bunny that had a fairly uniform accretion of material from its orbital zone. Due to the melting and vaporization, a lot of the heavier material sunk towards the center of the Earth, and that's a big factor in its structure. So today, the inner core is solid, mostly iron, a little bit of nickel. The outer core is liquid around the outer core. Beyond that is a mantle that has some flow. It's sort of a plastic type thing. Top of that is a silicate.
It's silly putty almost.
Yeah. And then beyond that. So the magnetic field of the Earth and believe me, any planets are done by the fact that you have sort of these unpaired electrons in a liquid outer core that generates a magnetic field. That's one model. I don't know if there's other models.
It's actually a question that I have about Like previously you mentioned that after the impact of Theia, the material forming the moon came a lot of that material came from the Earth's mantle. So basically, that would suggest that the Earth ended up with a proportionally more iron compared to before the impact.
Yes.
So
Yes.
so it's a very interesting thing to suggest how this affected the Earth. Like, does this extra iron means or explains why Earth has a magnetic field compared to Venus? Because Venus is similar in size, but it doesn't have a magnetic field, or at least not as strong as Earth. Yeah.
This may be more of a for questions for geologists for a future episode, but is there a reason why the four layers of the Earth is like it is? The core, the outer core, the mantle, and the crust. Is there a reason why?
As I just explained, this slide here is differentiation.
Okay.
Yeah. It also depends on the temperature. Like the crust, I believe the crust and the mantle is mostly the same material, but the crust is just solidified. That's mostly the difference. Yeah. Although okay, but although I think also there is some differentiation even there, because there's a difference between continental and oceanic crust, of course.
But that's getting a bit more finer detail of that for Earth. But again, a lot of stuff explains. We have explained a number of fairly important things, such as, for example, the axial tilt. Right, Earth's axis is tilted at 23.5 degrees. It's 23.4 and change, but call it 23.5 degrees. And that in part is due to the whatever Theia did, the angular change of angular rotation ended up causing the Earth to shift.
Someone is
then
asking,
the moon's or inclination around Earth is 5 degrees is also from that original set, so they can propose. But in terms of dense material, if Theia had a core, it wasn't very large, and it probably ended up merging with the Earth. And the result is the moon doesn't have an iron core, so it never developed a magnetic dynamo around it. And as a result, any kind of outgassing that occurred as the moon was cooling, the solar wind stripped it away, because you need a magnetic bubble to help shield you from the solar wind of the planet, as well as
also
gravity
gravity.
Go ahead.
And also the gravity to hold the atmosphere. Yeah.
Right.
But there was also someone in the live chat who says that he was under the impression that the moon and the Earth had similar composition. But of course, there are some notable differences between the Earth and the moon. Yeah.
So they have similar composition in terms of their surface materials, and the Earth's mantle and the moon share a similar composition. But the Theia collision didn't deliver to the moon, that outer blob, enough iron for it to build its own core and differentiate. It's smaller, so it cooled faster. The moon's smaller, so it cooled faster. It outgassed. Not having enough mass meant that gas didn't stick around very well. And then the solar wind dries away the rest of the thing, resulting in the moon not having an atmosphere. So you don't have the weathering that you do on Earth, as an example. That's why, astronauts' footprints on the surface of the moon will last for many millions of years, because there's very little to disturb the surface. And also mention, with regards to this thing, that the moon itself is also became sort of so-called tidally locked. That's a bad term, but essentially, the asymmetry of the moon, the moon's orbit orbits the Earth about once every 27 days, and it spins around on its axis about once every 27 days. The result is it has one face always facing towards us. It also is but that process. There's a tidal force process going on, which not only creates tides of the of the ocean, as well as the rocks have some flexibility.
I
But it
also
also
believe that
causes the moon is causing the moon to migrate out at a rate about once about it's about it moves the moon's moving away from the Earth about the rate that your fingernail grows.
I also believe the moon is like asymmetrical when it comes to density. Like the one facing us is probably slightly more denser than the one facing away.
Correct.
Yeah.
That's part of how that process goes there. There's the complex process of getting, quote, tidally locked, unquote, which is not a lock, but it's tidally facing is a complex process.
Eventually, the Earth will also be tidally locked to the moon, and one side of the Earth will always face the moon. That will take a much longer time. I don't know if the sun will die before that.
I think the sun will probably disrupt the Earth before the Earth has a chance to really have its day go down to 1 month.
And the rate at which that happens, it affects how fast the Earth rotates. It's like slowly slowing down, but it's very chaotic how that happens. For one thing, it would happen more slowly if you didn't have the oceans, because the oceans sort of slosh around and kind of act as a drag.
Yes.
On the Earth, slowing it down a little bit.
Yeah, there's also I believe the position of the continents also have an effect on this because of that reason. Like if you have different continental positions, then the tides of the water has a different effect on the moon as well. Yeah.
Sure. And finally, the Earth is maintaining an atmosphere in part. Its atmosphere is mostly nitrogen and oxygen. A bit of argon would be sort of the third thing, and then traces of other stuff, like water vapor. The very lightest gases, hydrogen, helium, actually escape into space. Earth is slowly losing hydrogen and helium, hydrogen gas and helium gas. Stuff that's trapped into rocks stay trapped into rocks unless you go and crush a rock or disturb it, or a volcano ejects it. But Earth's magnetic field helps minimize the ability of the solar wind. If anyone saw the impacting atmosphere, if anyone saw the big auroras like I did the other day, that's one of those cases where you can get extreme bursts from the sun that can begin to penetrate in to reach the upper atmosphere of the Earth. But normally the Earth is able to shield us from the solar wind, whereas Moon didn't end up with a much of an iron core, did not develop much of a dynamo. When rocks outgassed on the Moon, the Moon's lack of gravity allowed that gas to escape, and the solar wind stripped it away. That's not happened on the Earth.
Is the magnetic pole of Earth is not aligned precisely with the rotation pole,
and in fact, the actual the orientation of the domains in the dynamo are tend to be aligned with the rotation, but are not bound by that, and they'll flip back and forth.
They tend to be aligned. They're more stable, but they do flip back and forth. Are they aligned at all in any noticeable way, like with like the orbit? Like do the magnetic fields tend to, when they're not flipping, tend to be more aligned, like perpendicular to?
No, I mean, if you talk about the orbit of the solar system in terms of what the sun is, because the sun is the dominant mass.
Yeah.
And so if you try to measure the sun's equator, you find that Earth is actually I think we're about 3 degrees off, if I recall correctly, from the sun's equator.
Okay.
We call it 0 because we're Earth-centric, and so we say that's the origin of the solar system, is our path. But from a mass point of view, Earth is I think it's about 3 degrees off. Is that right? Is it 3? I think so.
Like I believe the reason why, or I would guess the reason why the Earth's magnetic field is almost ish aligned with the Earth's rotation is because of the Coriolis effect. Like when like the outer core is molten, as you
Well,
mentioned
I
before,
mean,
and
it's
so
more
yeah,
stable there. It's not
yeah.
Coriolis, but it's a more stable thing. It's not Coriolis is
Like I'm,
different.
but if I'm not mistaken, like the the iron core or the outer core of the iron core is convecting, and when it convects, it's affected by the Coriolis effect, and that probably is the reason why it aligns with the Earth's rotation, why the magnetic field aligns or tends to align
Okay.
with the Earth's rotation, perhaps. Yeah.
Okay, so that's the thing today. So so we've gone from these, protostar systems with supernovae and other and neutron stars, seeding them with heavier materials. We've seen shock waves, often come from supernovae, but can also come from active galactic nuclei and other stars um, um, switching on. Begin to get shock waves that crush things down. The angular momentum differentiates stuff. You got a star in the center and material on the outside that they accrete. They start with the little pebbles and they turn into planetesimals that accrete to form large planets. In the case of Earth, what happened was that we what's happening? Why is it switching?
Oh, I was doing that.
Sorry, stop it, please. So we're in a situation where we have I'm trying to remember where I was going. So
There was a
continue.
supernova. There was a supernova that helped form the sun by causing sort of a perturbation that led to this collapse, and that happened as an estimated 4.8 to 4.7 billion years ago. And then the process of actually forming a protostar takes on the order of a couple hundred million years. And the question of exactly, I think, when do you define the solar system as now existing when it previously did not exist is, I think, an ill-posed one. I think the closest answer might be like when fusion started, which I guess is probably, do we think that happened around 4.6
Yes,
or
about
so
4.6 billion years ago. So and that process of collapse, the collapse process was coming from the fact that we have two distributions of elements on Earth. It's called bimodal. When supernovae tend to generate material, they tend to have a kind of a distribution of isotopes. And Earth seemed to have two different isotopes laid on top of it, which suggests that there was probably a supernovae that occurred around 4.8 billion years ago of a star exploding. That shockwave began to collapse the molecular cloud, the cloud of mostly hydrogen helium gas, that of which the sun began to form. 100 million years later, that is 4.7 billion years ago, a second star went supernovae, and with that sort of protostar nodule, like you saw in those other diagrams, being there, that was able to catch a lot more material, particularly a lot of the stuff. So the first thing seeded likely with material, because a lot of that material passes through the gas clouds. The second one, now being in protatory form, nodule, caught a lot more material from the second supernova that occurred. It took about 100 million years for that result of things to end up generating enough fusion that the sun, quote, switched on. And about 500 million years later, there was enough material to form what you sort of call Earth. But it had one last little hurrah where Thea hit it, and Earth Moon thing formed, and we end up with Earth Moon.
Beautiful.
So if you want to move to a different spot, go ahead now. You can.
No, that's it. That was the end of the. That's the end.
Oh, yeah, that's yeah. Those are just slides that we never used.
Yeah.
Yeah, this is the last slide.
Yeah.
Oh, I one thing I could mention, like you mentioned that the Earth has a magnetic field which slows down the escape of hydrogen and such from the Earth's atmosphere. But there's an interesting thing about Mars. Like Mars used to have water on its surface, which is pretty indicative from the features it has. That it is like these places where there were once waterfalls and such, and an ocean basins and such. And what probably happened on Mars is that as it was blasted with the radiation from the sun, the water H2O was split into hydrogen and oxygen, and the hydrogen escaped while the oxygen was left behind, rusting the Mars red, and that's why Mars is
if I
red.
can inject in, if I can inject in there. So the thing you're missing that's critical is that the mass of Mars is only about 1/10 the Earth.
Also true, yeah.
So things like oxygen at even Mars cold temperature achieves escape velocity, right? That not only can Mars not hold on to its hydrogen, but it cannot hold on to its oxygen.
Mhm.
And even water molecules have, their ability to get split apart by what? This ultraviolet light from the sun, because you don't have a appreciable ozone layer. You don't have much of a magnetic field on Mars. The result is that the oxygen leaves. And so people that say, "Oh, we're going to terraform Mars," fail to realize the reason why Mars doesn't have an atmosphere is it can't hold on to it. The reason why it does not have a bunch of water in Mars's atmosphere is that it can't hold onto it, right? So even if you were somehow able to magically create some nice oxygen water vapor around Mars, it'd only be temporary. It would leak into space.
Yeah.
Is there any way
to blow it away?
Instead of Mars, is there any way to cool down the atmosphere of Venus?
Big mirrors in orbit around Venus.
Anyways, I have some questions in chat.
Sure.
I've been going back. Here's one question.
Read it so that people that aren't watching can hear.
I've heard it suggested that Jupiter's large mass protects against more frequent destructive events from asteroids or otherwise could collide.
Well, certainly Jupiter is a big, attractive gravitationally. A lot of objects can hit Jupiter and to some extent Saturn. So they certainly are a convenient target. If you think about the mass of our solar system outside the sun, I believe Jupiter's around 78% of the mass that's not in the sun. So it's the big heavyweight, and therefore it can attract a lot more objects. On the other hand, Jupiter can also throw things inward, so it's not always nicely protecting us, but it certainly is a big target and a big gravitational attractor.
Did we observe an impact on Jupiter like many decades ago?
In fact, I had the privilege of watching that in a 8-meter telescope, and actually saw the plume move beyond the edge of Jupiter because the impact was unfortunately just behind our view line. But Jupiter rotates quite fast, and so between the material ejecting out above Jupiter's atmosphere and it rotating, you actually saw the plume move out.
I've also a question
Shoemaker
about
DV9 was the original object that got shredded tidally, and then
is that the one where people made the cult to die? Everyone died.
I don't know, and those sort of things I tend not to. Yeah, that's someone else can get that fact. I'm not interested.
So next question was, so does that mean it's too late for any of the planetesimals to eventually grow big enough to clean up the Kuiper belt?
There's a lot less material flowing around there than it was at one time. Some of those things do accrete, but there isn't enough. There doesn't appear to be enough. And even the Kuiper belt, we're talking about the belt that sort of the material that sort of ends at the inside the outside edge of Neptune's orbit, where Pluto, being a member, it sort of skirts the inner part of it. And there's not enough. The material is now thinned out. A lot of our dwarf planets have already accreted a lot of material, but they're so scattered, it'd be very difficult for them to accrete to form a more significant planet.
Like I would guess that like in order for it to be cleaned up, is you have like one object has to reach a critical mass in order for it to clean everything up, basically.
Yes,
and if you
and you have to have time.
Yes, also
Enough material and then there has to be enough density of things that can accrete to that mass too. So,
all right, see, like 2 more questions I can find. It says, what would happen if a supernova and gamma ray burst with the collide?
So a gamma ray burst were to hit a supernovae.
I don't know that much of anything would happen.
I'm trying to think of anything would really happen, because the supernovae is going to be the dominant action, right? When the star is collapsing, and it collapses very fast, right? Once it loses its internal pressure, right? It starts fusing iron, and it collapses in a very fast. I mean, as then the outer layers get to be some notable fraction of the speed of light when they slam into the inside, and isn't it like a matter of minutes to seconds?
It's very fast. I think it depends on the details of which type of supernova.
Yeah.
But yeah, they can go.
And so a gamma ray burst is going to be a beam of gamma rays, and the supernova is going to start happen fairly fast, and the gamma ray burst would just probably annoy the material. Supernovae.
But I mean, you're going to be getting a lot of gamma rays from the supernova. Like,
true.
The gamma ray bursts, the reason that they're still so like intense is because they're collimated. But I assume a supernova, I would bet a lot of money that it's also just a very bright source, probably much brighter than the gamma ray burst. So
and then the stuff it ejects out, like isn't it nickel, so forth, the radioactive decay? You got a lot of material that's very decaying, and you're getting all kinds of gamma stuff going there. So supernovae tend to be bright in their gamma stuff as well.
Yeah, I think that's all the previous questions I can find in the chat that we missed answering during the thing.
I also wanted to just say we don't know. I don't believe we have a solid, firm understanding of what causes gamma ray burst. There's like a lot of options, but them and like fast radio bursts, they're not totally.
They do tend to form the poles, right? They eject from the North Pole and the South Pole of the rotating star, right?
But there's also gamma ray bursts that can be formed through other processes potentially as well, and magnetars and so forth. So it's an active area, slow and fast bursts. It's a truly active area of research, which means we're learning. We don't know enough yet. But
so wrapping this up real fast, I just want to say if you have any more questions. We will be having a after show on the 22nd of June 22nd again, 1900 7 p.m. Eastern, 1600 4 p.m. Pacific.
And that's on June
22nd.
22nd.
And if I can get my computer working, I'm going to try to download all these videos to make one big movie before that happens. So have all this in one big movie thing. But other than that, anything you guys want to advertise that you're coming up in the future?
I will be appearing tomorrow on Bad Science Sunday. It's going to be wonderful.
That's going to be a fun thing. The Unnamed Tavern is on the 25th. And it's a interesting show with Dapper and Manya and Chesh, and we talk about politics and weird things of the day. I believe that's on May 25th. I think the time there is 15:30, 3:30 Pacific. There's also a volcano show I run. We do a thing about once a month, talking about what's happening with the killer volcano. And that's going to be on June 7th. And the Volcano Show will start at 1 p.m. or 13 Pacific time again on Shesh's channel.
Right. Ness, anything on
I'm mostly active on Jackson Wheat's channel. So whenever he is active, I often join his live stream, and I also write or help with scripts for his videos. So
Yeah,
go check him out.
As for me, next week we'll be going from realistic science to mythical science as we talk about the MCU Thor movies. And then in 2 weeks, we will be talking about the only living dinosaurs, the theropods.
Yeah.
AKA birds.
Yeah. So again, if you have questions for us for the thing, and let's say you're either shy or you don't want to you can submit it ahead of time by putting your questions in the link below. So he will check there for this thing for questions, or you can show up live in the audience. There won't be really a presentation. It'll just say, hey, we've had before Earth from the early Big Bang up till now. So please be ready to have your questions, and we'll give you that. We'll give you the answers that we think might be plausible. Of course, you have corrections as well. You can correct us.
We have one last question. Why does Scooby-Doo have retractable claws?
Quantum physics.
Doesn't Scooby-Doo, being a dog, don't dogs have retractable claws? Or
No, they don't. Dogs do not have retractable claws.
They don't.
That's why it's confusing. Why it's Scooby-Doo.
This is why I'm not a biologist. I'm not a.
In cartoons, every animal is a cat, basically.
One last thing, if there's any
I learned something. Thank you very much.
One last thing, if there's any geologists out there who want to, now that Earth is here, that want to continue this series post Earth or during Earth for an Earth mini series, give me a call or have them contact me so we can continue this series since Earth is here now. But anyways.
Well, thank you very much for putting up with these 5 shows and all of our errors, and hopefully you corrected things and you learned something. I did too, which is dogs don't have retractable claws. So.
I actually have a fun fact. There is actually a transitional dog in the fossil record which has partially retractable claws, because that's an ancestral trait that modern dogs lost.
Anyways, all right. If you haven't subscribed to these 3 people yet, do so. Always fun content, and see them on other channels. But until then, never stop learning and enjoy the randomness. We will see you next time. Bye.
Bye.